Hello and welcome to the Unit 8 Section 1 video on identifying circles. So identifying a circle is easy enough, but we are also going to be identifying things that intersect circles, and that's really what this section is about. Is we have lines and line segments that are going to intersect circles, and they all have special names. So first of all, a circle is a set of all points in a plane that are equidistant from a given point, called the center of the circle. So you basically have all the points that are the same distance from the center, and you connect all those points together, and you end up with a circle. And this is going to be an infinite number of points, okay? A circle with a center C is called circle C, or you can use the notation that you see here. Now, the interior of a circle is a set of all points inside of a circle. The exterior of a circle are all the points outside the circle, okay? Simple enough. So, let's talk about lines and segments that intersect circles. A chord is a segment whose endpoints lie on the circle. So, here you have chord AB or segment AB. This is your chord because it ends at the circle's edges, okay, or at the circle itself. A secant is a line that intersects a circle at 2 points, okay? So here we have a line. Remember, a line goes infinitely in both directions. So line L is the secant because it goes through 2 points on the circle. A tangent is a line in the same plane as a circle that intersects it at exactly 1 point. So a secant, you intersect it at 2 points. A tangent, you only come in, touch the circle at 1 point, and then you continue on. And a tangent line, also going to be going infinitely in both directions. The point where the tangent and a circle intersect is called the point of tangency, and that is point C here. So, for example 1, let's identify each line or segment that intersects circle A. So we have 2 chords here, and remember, a chord is a segment that terminates on the circle itself on both ends. So we have 2 chords, the first of which is chord EF, and you're probably thinking, or line segment EF, and you're probably thinking, well, this is a line, this is not a line segment. Remember, you can have a line segment be part of a line. Okay, go back to Unit 1 and remember those very first basic concepts that we covered. So EF is a line segment and it is a chord. The diameter here, BC, is also a chord because it terminates on both ends. So tangent, or the chord here, is BC or CB. You can say it both ways. Now the tangent line that only hits at one spot, that is line L. Let me write that a little bit nicer. Line L. Now the radius. The radius is a segment that goes from the center to the edge of a circle. So we have 2 radii, or radiuses, and that is AC and AB. AC and AB. And those are going to be segments again. Now the secant line is line EF. Now here it is important to write the notation correctly. This is a line, the chord was a line segment. And then the diameter, BC, is the line that goes all the way across and through the center of the circle. Now remember, the terms radius and diameter may refer to line segments or the lengths of the segment. So lines and segments that intersect circles. 2 circles are congruent circles if and only if they have congruent radiuses, okay? So if AC is the same as BC, then the 2 circles, circle A and circle B, are going to be the same. Concentric circles are coplanar circles with the same center, and 2 coplanar circles that intersect at exactly 1 point are called tangent circles. So here we have internally tangent circles, here we have externally tangent circles. So now let's talk about using the properties of tangents. A common tangent is a line that is tangent to two circles. So here we have line L that is tangent to both circle A and B. Line M is also tangent to circles A and B. They touch each of the circles only once. These are external tangents. Now lines P and Q are internal tangents because we are tangent to A on one side of the circle and tangent to B on the other side of the circle. So here's one way to look at it. In the external tangents, the circles are on the same side of the line. But in internal tangents, the circles are on different sides of the line. A tangent line is perpendicular to the radius at the point of tangency. This fact is the basis for the following theorem. So if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So if I have a tangent line L and I draw a radius from the center of the circle to that tangent line, then the radius and the tangent line are going to be perpendicular. If a line is perpendicular to a radius of a circle at a point on the circle, then the line is tangent to the circle. So here, because we have CD, the tangent line, M, is tangent to circle C because we have formed a perpendicular relationship. So these two are sort of opposites from one another. And then the last theorem, if two segments are tangent to a circle from the same external point, then the segments are congruent. So if we have a tangent segment AB, where B is where we touch the circle, and the only place where we touch the circle, and then we go from A to another point, C, where C is also the tangent point of tangency, then AB and AC are going to be congruent to one another. And that is what we're going to use to do this final example. So DE and DF are tangent to circle C. So we want to find what DF is. Well, if we know that these two are tangent to one another, or both tangent to the circle, we know that they are congruent to one another. So DE is going to be the same as EF. So DE, the length of DE is the same as the length of DF. Okay? So the length of DE is 5y minus 28. The length of DF is 3y. So we subtract 3y from each side, add 28 to each side, and then divide by 2, and you get y equals 14. So to find DF, we know that DF is 3 times y, so that's 3 times 14. So DF is going to be 42. All right, so that finishes off kind of our introduction to circles and the parts of circles. Coming up in the next section, we're going to talk about sectors of circles.